Hi, and welcome back to Introduction to Deep Learning. Today, it's already the last exercise tutorial session. And in this one, we are going to talk about sentiment analysis with RNNs. That's the main topic. And as usual, let's go over the outline of today. So first, I quickly want to talk about the online exam. It's not too much new information there. Then quickly recap the exercise 10 on semantic segmentation. And as the previous times, I want to show case studies of student solutions. And then we quickly recap the concepts of RNNs and LSTMs. And finally, we are going to introduce the final exercise, which is on sentiment analysis with RNNs. So as you all know by now, the exam will be online due to the current situation and restriction at the university. And as usual, there is no retake exam for this course because this class is taught every semester. So you can just take it next semester again. For the bonus, this will be transferred to any future versions of this class. Also, if you've taken the class in previous semesters and you obtain the bonus, you can have it transferred to this semester. And the organization, we will release more information soon on Piazza, as soon as we have them. And yeah, the relevant content are obviously the lectures and also the exercise content, including the optional notebooks. So yeah, the exercises will also be relevant for the exam. All right, let's continue with the recap of exercise 10 on semantic segmentation. The goal of this exercise was that for a given input image, we want to assign a label to each of the input pixels. So that basically means that we want to predict a segmentation mask, which has the same shape as the input image. So down here, you can see an example of such a segmentation mask. And here, different colors denote different object classes. So blue correspond to cars, for example, red to persons, and so on. And yeah, here we provided you with the small data set, which contained 23 classes and nearly 600 images with segmentation crammed with information. Because the training set is pretty small, we also wanted to introduce the concept of transfer learning and apply it to this exercise. So the idea for semantic segmentation usually is that you have an encoder-decoder structure. And here, together with transfer learning, we wanted to use classification network as an encoder. And here the idea is that a CNN or any network that is trained on a huge data set, for example, for image classification, then encodes meaningful information that then also can be used in our task. So the usual approach here is that we train our classification network on a huge image data set, and you have like an encoder structure like this. So yeah, a bunch of convolutions which go down, and finally you end up with like a feature vector and then the final classification part. So the first part can be thought of as a feature extractor. And we want to use this feature extractor and apply it in our small data set and optionally freeze parts of it. And we hope that because of training on this huge data set, it contains also useful features in our case. So yeah, as I said, we use the encoder part or feature extractor part of this image classification network, use it as an encoder for our encoder-decoder structure, and the decoder part of the architecture can then probably be mirrored or pretty similar to the encoder. Yeah, basically having upsampling layers or transpose convolutions to go back to the original size of the image. And then per pixel classifying the labels. Here you can see the leaderboards from previous semester and this semester. One thing to highlight here is quite nice that First, like the scores are pretty similar, but we could achieve a slightly higher score. So you managed to beat the last one semester. And yeah, the scores are pretty remarkable. And yeah, so first, congrats to the students achieving such high scores. And yeah, actually, like the top one submission here only slipped in at the very few last minutes. And for that, we want to review the first two submissions. The first one achieved a score of 92.06, and the second one, 91.72% accuracy. The top one submission is a pretty straightforward architecture in itself. So as most of you did, the student used MobileNet version 2 as a feature extractor and used the features which were pre-trained. The decoder is pretty simple in itself, actually. So it only consists of a few upsample or transpose convolutional layers and some batch norm and ReLU layers. It's a bit unconventional, the order of upsample and transpose convolution and convolution itself, but it seems to work well. Another thing which is a bit uncommon is like this bicubic upsampling mode. But yeah, unfortunately, I don't have the hyperparameters for learning rate, etc. But at least like having such a simple decoder architecture and possibly good set of hyperparameters can already achieve like the top one score. To summarize this submission, the top one submission, yeah, it's an encoder-decoder architecture. The encoder is pre-trained with a MobileNet, and the decoder is, yeah, pretty simple with upsample layers, transpose convolution, batch norm, and ReLU. So nothing too fancy, but it still seems to work quite well. The second submission is a bit more complex. It also uses like this encoder pre-trained mobile V2 network. And then we see several different parts which were defined in the architecture. So here we have like an inner part, then we have a series of transpose convolutional layers with different input and output features. And then we also have like a series of decoder layers, which are defined here as lists. So this lists go on. And this network architecture then actually defines a unit architecture. So here is the forward pass. And if we go through it step by step, we see that the student doesn't directly use the entire forward function of the entire encoder, but actually iterates of the encoder itself, so over the layers of the encoder. And where is it? Yeah, directly uses the layer and forwards the input or the output of the respective layer through the current layer. But the student also saves the result and the features at this particular layer. So here we can see that the layers are appended to a list, or the features are appended to a list. And we can reuse them later on. Then, yeah, we saw that we also have this inner block, which consists of a bunch of convolutional layer, batch norm, ReLU. And yeah, that's basically the inner part of the unit. And the interesting part is now at the decoder part. So here again, we iterate over the upsample layers, which were defined here simply as this list of transpose convolutions. And yeah, then we forward our current result through the layer. And the interesting part of the unit is that we concatenate the current features from the decoder with the corresponding features from the encoder. and yeah, pass this on through the next layer. So here on the left-hand side, you see an illustration of the unit, which you already know from the lecture. So this roughly corresponds to the structure of this network here. So on the left-hand side, we have the encoder part, where we go down in resolution. And down here, we have the inner part. And then finally, we have the decoder part, and these gray arrows are first like the saving of the encoder features, but also the concatenation part. So here, you always have to make sure that your feature dimensions are correct. So basically, because now we have like the features from the encoder and the features from the previous decoder stage. So here, the input features can be sometimes a little bit tricky, and you have to make sure that this matches your final dimension of the encoder and decoder features. And then you finally go up and at the end have your segmentation output. To summarize, the submission uses a unit architecture. The encoder is pre-trained on image classification. And the decoder then uses transpose convolution, batch normalization, and I think also ReLU, but no dropout. And in the forward pass, what you always have to make sure for a unit architecture is that you concatenate or use the features from the encoder in the decoder part in your forward pass. All right, with this slide, I quickly want to show you when and what to fine-tune in a network when we do transfer learning. So here on the left-hand side, we have a diagram with two axes regarding the dataset similarity between the pre-trained and our current dataset, and also the axis about the dataset size itself. On the right-hand side, we have the same setup, and here we see different models of an feature extractor, the large first part, and basically the task-specific network, either as a classifier for image classification or in our case for semantic segmentation. So now we have 4 different cases, and let's quickly go through them step by step. So the best case for our target task is if we still have a large data set, but the pre-trained model was trained on a quite different data set. In that case, you would most likely train the entire model. So basically, we don't freeze any layers in our model and train the entire thing. The second case is if we have a large data set, and it is actually quite similar to the dataset which was used to pre-train the model. In that case, we can, for example, freeze some of the first layers and only train the last part of the network. Then case number 3 would be that we have a small dataset in our target task, and it was also quite different from the pre-trained model. In that case, we have to train a bit more of the dataset of the model itself, because the pre-trained model was not that suitable. But to prevent overfitting, we still can try to freeze some of the earlier layers, which usually, like for CNNs, usually extract like low-level features, and these should usually still be quite similar between image datasets. And the last case would be that we have a small dataset, and it's quite similar to the pre-trained model. And in that case, we can, for example, freeze the entire convolutional base and only train the second part or the feature, the classifier or the decoder. I hope this slide gives you a quick and easy idea of which part to freeze or train in different cases when we have different dataset sizes and similarities to the target task or the pre-trained task. Let's continue with the main topic of today's tutorial, and it's about recurrent neural networks. So far we looked at fixed size vector as inputs, or like fixed size matrices. So for example, like a fixed set of features of houses to predict the house price, or images which also had always like the same size. And we fed this through a network. But now we want to consider new types of input, and especially like sequential data or like a series of input data. And the interesting thing here is that there's no predetermined limit on the input size, basically the length of the series. And to give you a few examples of these types of data could, for example, be a series of images, which will lead to videos, or also a series of words, and this we can consider as text. One straightforward approach to tackle like the series of input points would be to use a straightforward neural network and just apply it on every single item in our sequence. And here you can see such an example. For example, for each point in our input data, we individually apply the network itself to get like an independent output. And yeah, we repeat this for all the input items. However, the problem is that usually like for these kinds of sequential data, they depend on the previous components. So that means that the elements or the items in our series usually relate to each other. And this relationship we cannot handle by applying them individually and forwarding through our neural network. So with recurrent neural networks, we want to exactly capture this relationship between the input points. And that means that during the learning process, basically the relationship or the samples themselves, they are not independent. So the main point for RNNs is that when we train them, we can remember elements or things from the previous training data or from the previous inputs. And also that previous inputs can influence the outputs of the current samples. So to rephrase it, in other words, the RNN produces different outputs for the same input, depending, however, on the previous outputs in the series. So from the lecture, you should know like this figure, which means like for a certain input at time step t, we fit it through the network. And here, basically, this arrow around it means that we incorporate the information from previous steps. And then we output the output state or the hidden state. And to show this again is basically the output always depends on the input, but also on the previous hidden state. One important concept of RNNs is parameter sharing. So the idea is that for a single training step and all items in our training sequence, we apply the same weights to all input items. So this has the advantage that we don't need to define the length of the series beforehand. This figure basically shows this quite well. So because we have like this hidden unit in the middle and we have the same weights, for the entire series we can repeat this, but still capture the relationship to previous samples or input items by incorporating the hidden state. And that basically means that for each input samples in our series, it undergoes a different procedure with the same weights, however. Now we can think of different cases and concepts of input and output data. So here we have 5 different cases where we have a different set of input items or data and a certain target. And one of the simple cases which we were focusing mostly by now is like this one-to-one relationship. So we have one input sample, like an image, for example, and we also want to have one fixed output for this input sample. So here we have a one-to-one relationship. The second case would be a one-to-many relationship. So one example here could be that we have one single image as input, and we want to caption this image, basically giving a description of this image as a sequence of words. So as I said, the input is a single image, but the output is a sequence of words. So we have many outputs. The opposite would be that we have a many-to-one relationship between the input and the output data. And one example to give here is sentiment analysis, which is actually the exercise of this tutorial. So sentiment analysis has a sequence of words as input and a final classification, so a single output. And that's something which we're going to have a look later. Then we also have many-to-many relationships. For example, machine translation, where you have a sequence of words as input, and you also want to have a sequence of words as output. And the interesting thing here is that we have like a certain time shift. So like usually for machine translation, for some cases you cannot immediately translate it word by word, but you need some context of the input data to make a reasonable prediction. The final case could be a many-to-many relationship. For example, video classification on a frame level. So basically for each of the frames, we immediately want to do the classification. For example, checking if a frame shows a dog, for example. And here we can immediately perform this on a per frame basis. But still we have like a series, so many input points, but we also have many output points. One problem with RNNs is that they usually struggle to learn long-term relationships between the input samples. One approach to tackle this downside of RNNs are LSTMs, and this stands for long short-term memory networks. And these are special kinds of RNNs which have a slight change in the architecture, but they are actually able to learn these long-term relations. And if we compare different cases, so here on the left side, we have a rather short sentence, and on the right-hand side, we have a pretty long sentence. And if we first look at the left, the sentence is "clouds are in the sky." And here, the interesting idea is that the word cloud or clouds and sky are highly related. And because the sentence is so short, it's usually still, so the RNN is usually still able to capture this relationship between clouds and sky. On the right-hand side, we have like the sentence, "I moved to Germany," then a long part in the middle, "so I speak German fluently." And the main related concepts here are the word Germany and the word German. So these are highly related and coupled basically. But because they are so far away in the input sequence, RNNs usually struggle to capture this relationship because they are so far apart. And LSTMs then basically, with some changes in the architecture, are usually able to handle this kind of relationships, even if they are far apart. All right, let's continue with the exercise itself. So as I said, this is going to be about sentiment analysis. The goal of this exercise is, given a sequence of input words, so a description or review in our case, to predict the outcome if this text is positive or negative. So here we have two different examples, and as I said, the input is a sequence of words, and the output is basically positive or negative. And here, we have reviews of movies from a certain data set, and these reviews can be positive or negative. One quick note on the content of the exercise itself. So don't be shocked when you open up the zip, because this time we actually have 3 notebooks, 2 mandatory ones and 1 optional one. And the first notebook itself is only about the text preprocessing and the embedding. So that's quite important because this time we have text data compared to image data which we had previously. So here we guide you step by step how to preprocess this text data and the corresponding embeddings. So this is necessary. So we have our data ready. The second notebook then is on the implementation itself of the sentiment analysis task. And we also have an optional notebook where we basically allow you to implement the RNN or the LSTM module yourself. So as I said, the first notebook is only about the data preprocessing, but also on the embedding layer. So because we are switching from image data to sequence of words and text, which means text data, we have this as a separate notebook. And yeah, the data set which we're going to use is like this IMDb sentiment analysis data set. And yeah, the goal is to prepare the data which we're going to use and also to implement the embedding layer. For notebook 2, this is about the implementation of the network itself. So the architecture consists of the embedding layer, which we implemented in notebook 1. For the main part of the network, we allow you to use the PyTorch implementations for RNNs or LSTMs, but you also can use your own implementation from the optional notebook. And then finally, we have like the final output layer, and we want to train this for classification of the sentiment of this review. And yeah, the performance measure or the metric here is simply accuracy. And yeah, to summarize, the goal of this notebook is that you implement and train such a recurrent neural network for the task of sentiment analysis. The details about the submission is that, as usual, it starts today at 1 p.m., so June 24th. The deadline is June 30 at the usual time at 4 p.m. And yeah, submit your trained model as usual. And yeah, we have the accuracy as the main metric. So this time again, you have to pass the threshold, which is 83 on our submission test set. To summarize, on Monday, you should watch lecture number 12. This is on advanced deep learning topics. So this is usually really nice because it's a fast forward of different advanced topics, such as GANs, variational autoencoders, graph neural networks, which is really interesting. Yeah, quite different topics here, and these are really fascinating advanced topics. And then until Wednesday, you should submit this exercise here on sentiment analysis. This is also already the last tutorial session. So I really hope that if you think back from the first few exercises till now, what you have achieved so far. So basically starting from very basic data preprocessing stuff and getting familiar with the terminology to train your first neural networks until now to even like slightly advanced topics of different data inputs such as text. So yeah, that's basically the wrap for this tutorial session. I really hope that you learned some new things and also had fun doing the exercises. With that, I wish you good luck with the last exercise. And yeah, as I said in the beginning, as soon we know more details about the exam, we will let you know. But for now, yeah, happy coding with the last exercise.